Thank you. I will break the streak of speakers whose name is Jānis. I'm not Jānis, my name is Atis Straujums. I'm a security architect at the company Zimperium. And today I want you to take away the idea that what white box cryptography is and what it can do, and that there is this one tiny piece of magic that still can protect your secrets when all else is lost. So that's about today. First we'll look at the real-world cases where white box cryptography is useful. Then I'll tell what white box cryptography is, and tell about different white box attack model, about key extraction methods, the small demo, and then give an intuitive example of how white box cryptography can work, so that you start believing that it is at all possible, because at first it sounds kind of crazy and impossible. And then a shameless plug at the end about our product, just to explain how that looks for the users. So there are a couple of use cases which I'll just mention. Imagine digital rights management. You probably are watching some Netflix on your browser or some other streaming provider, and the movie that comes to your browser is encrypted. And Netflix and other providers, they don't want the movie to be decrypted to clear, but they still want the movie to be decrypted when you watch it, because otherwise you can't watch it. So what is necessary is to have this encryption key that decrypts the movie to be used on your device in a way that the key doesn't leak. Because you may not be a legal user or legitimate user, but you might be an attacker who's trying to find the key for the movie and then stream or either publish the movie without encryption. So this is one case when key is necessary to be protected, but still used in a device which is potentially under control of attackers. Then there are mobile payments use cases. Nowadays it's becoming more popular that you can take your card, swipe to the merchant's phone, and the merchant can accept payment on a normal mobile phone. There's no need for a POS terminal or something, but you have to enter your PIN code on their device, and there is some cryptography going on merchant's device, which a malicious merchant might want to intercept and maybe steal some data from your card. And then there is a generic use case about user or device authentication. If you want to authenticate between your mobile phone and a car, or between your mobile phone and an embedded medical device somewhere in your body, you want to have some authentication, and this authentication should happen using some cryptography with keys being protected as much as possible. So all these use cases share the same situation, or the same aspect, that cryptography has to happen on a device where attackers potentially have full control over. So attackers may control everything on that device, and you still want to do something that is secure enough. So that is called white box cryptography, and white box cryptography protects keys against white box attacks. Right, you will say white box cryptography, white box attacks, so circular definition, we can do better. So white box cryptography means that keys are protected even in the white box attack model. And white box attack model means that we are facing a capable attacker which has control over your device. They can read memory, they can access firmware, they can control code execution, they can do everything. Yet you still want to do something secure. These capable attackers, they have multitude of tools available. They have debuggers, decompilers, custom kernels, hardware emulators, whatnot. So, and what we want to do something securely in this environment. Those attackers, they may try to attack different things on your device and your application. They can try to steal intellectual property from the application. They can try to just misuse your device to just use the resources of your device. They can try to steal your identity. But today I'll focus on one target asset for those attackers. That would be cryptographic keys. So there are several types of keys, and keys are used in many places and in many ways. Previous speakers discussed keys in several use cases, and there are some ways how the keys can be extracted by attackers. If a key is embedded in your application, in this case I'm talking about the applications not somewhere on the server side, but applications on your end device. So they can just reverse engineer your application. They can just look at the resources or binary code and try to find embedded secrets. Then they can also try to scan memory at runtime. When your application is running, they can just scan the memory and see whether there are some keys appearing in the memory. And for some other cases, there are side channel attacks. Typically, this side channel attack concept comes from hardware, where you can measure, say, a smart card, power consumption of a smart card, and when the smart card tries to encrypt something or sign something with a key, where the key has a 1, there's a higher consumption, and when the key is 0, then the power consumption is lower. So by measuring the power consumption of a smart card, you can see zeros and ones. Well, not as simple, but in concept. So that's called side channel attacks. For white box implementations or for your application running on a device, the side channel attacks are even more relevant because attackers don't need to measure your power consumption. They can just see the memory. So still, you want to protect against those. So a small demo. All right, so this is, I just use Firefox, it doesn't matter. Chrome, Edge, they are all the same.
Safari.
And I'll use one tool which can find keys in the running process. So, and what this tool does, it will take a little while, but what this tool does, it just takes the process memory and scans it for specific patterns, which represent, in this case, AES keys. AES is a symmetric cipher algorithm, and typical implementations, they store all the round keys. AES has 10 rounds, and they stores AES round keys one after the other. And because they are related to each other, this tool can just see in memory whether there are some locations where this happens. Well, these keys are not so sensitive, which are found. There are most likely some TLS keys for communications between the browser and the portal, or maybe some advertisements that are established in their own communications. So, but quite a few keys. So, with this demo, I just wanted to show that it is possible to just scan your device memory if you have access to it and extract some secrets. So,
you need some root or admin access to launch it, yeah?
Sorry?
You need root or some admin access to launch it.
Sorry, what's that?
You need root or some admin
Well,
access
yeah,
to
in this
launch
case,
it.
sure. You need to access. You need access to the memory of that process which you want to scan, sure. But that we are assuming that attackers are very capable in our white box model, so we assume that they have full control. They can do everything. So, well, if we have such a situation that we want to use cryptography on such a vulnerable device, so what do? We use white box cryptography. And here's just a simple conceptual explanation of how white box cryptography can work in general. Let's assume we have an insecure device where we want to do something. We want to do a small, simple mathematical operation. We want to add two numbers. But the device is insecure, but we don't want to show the attackers neither the two arguments nor the result. So what we can do, we can add two random numbers to each of the arguments. The random numbers only we know. And then we send those two numbers to our insecure device. The insecure device simply adds the two numbers together and returns the result. Because we know the two random numbers, the x and y, we can find out the real result. But the attackers, they just saw the two randomly looking arguments and as randomly looking result. So in this scenario, in this setup, attackers have no way of finding out what the real arguments were and what was the result. This type of encryption, if you will, is called homomorphic encryption, where you do the operation on encoded data without decoding the data. And since 2009, there is a theoretical result that so-called fully homomorphic encryption is possible. And that means that you can do multiplication and addition in such a manner that you can send the job to the server and the server will do the operations and will never know what data it used, what actual data it used. Only you know what the actual data were because you have the encryption key. So white box cryptography is kind of similar, but it has to do a bit more generic operations, and there are some more harsh requirements. For instance, you have to set data from clear into this white box environment and then get data out to clear on the device itself. So it's not as rosy as in this example.
How you exchanging X and Y's? How you exchanging X and Y's?
No, it's in this case it is you who control the X and Y's, and you also have the X and Y's afterwards. So you only send the data and the task to the server, and ask the server or the device to do something with these data, but you don't want the server to learn about these data. But you are in control of the X and Y, so you don't share it with anyone. You create X and Y, and you later use the X and Y.
Is it like a zero proof knowledge, zero knowledge proof concept?
Well, not exactly. Zero knowledge proof, you prove that you have done something without telling what exactly you did. In this case, you actually want to do something and get the result. You don't. It might be something that when you get the result from the server, you might want to know that the server actually did what you asked it to do. Then the server might try to prove that it did without any information, without giving you any information. But yeah, so a different concept. So this is the zKeyBox product from our company. I'm the product manager of that product. So I've been doing white box cryptography and similar technologies since last century, even before the white box cryptography had a name. But this library is just a library where you use standard algorithms, and the only difference is that you can use this library in insecure environments, and it keeps the keys secret. For static and dynamic keys, that's an important thing, that you can embed secrets in your application. The first speaker mentioned that if you embed a key inside your code or somewhere, then it can leak to the repositories. In this case, you can in fact embed a key which is protected in your application and then use it at runtime, and nobody can get the clear text value of the key. And so this is also what many customers are doing. They are embedding some authentication keys or attestation keys in their application, and then using those keys to establish some communications, and then get some dynamic keys also later during runtime from the server side. And also those dynamic keys then can be protected using this white box library. So, okay, many algorithms. One important aspect here is that all white box solutions are purely software based. So you don't need any trust zone or TE or SGX or any other hardware support for it. It is purely software based solution. The keys and the algorithms use some mathematical transformations so that they can work on those transformed keys, yet still perform the standard cryptography. So that's important, that it's completely software solution, and therefore also works on most platforms and withstands sophisticated attacks, also like these side channel attacks. Even for attackers who have full control over memory, they still can't get the key. So just to show, this is how the customer who wants to use our library, they just go to our website and build their schema, request that that package, and then they can use exactly this cryptographic scheme in their application. And all the white blue boxes, they represent different types of keys. This was in static. These all are others are dynamic keys, and all these keys are used on an end device, but they are all protected so that attackers can't see any one of those at runtime. So that's essentially it for me. The main takeaway I wanted you to have is that it is possible to process secrets on end devices which are completely vulnerable to attackers in a way that attackers cannot get hold of those secrets.
Is it like encryption in the runtime?
Sorry?
Encryption of the keys on the during the runtimes. The system understands, well, can use them, but they're useless to anyone who can see them apart from the system.
Correct. Those keys which are used at runtime, they are encoded in a way that our library or any whitebox library can operate on. And depending on the algorithm, the key encoding may be different because of different operations that are used. AES keys have one type of operations that need to be done with them. RSA has more math-oriented additions, multiplications, so that encoding may be different. But there is a match between how the key is represented and what the algorithms understand. And typically, every customer of ours, they get a different encoding, so they are not incompatible with each other.
But how this communication, for example, we have on this end device, we have our software, yes, which wants to use this cryptographic key, and how this communication between our software and your process.
Yeah, you use this library as you would use any other library. I mean, if you use OpenSSL or something, currently you can use this library. Well, it has a different API, but generally it's the same idea. You just use AES cipher, you use signature, you use whatever. The only difference is that the key object itself is not a clear text 16 bytes for AES. It is just an object. Similarly, how you would use, okay, for Java, for instance, for Java we have the so-called Java provider implemented. You don't even notice the difference. You just say that you want to use, instead of the default provider, you use our provider, and the rest is the same. So in that sense, you use it as a cryptography library.
And is this process actually occurs entirely on this device, or we need communication with some of your servers?
No. This is completely offline library. You embed it in your application and just use it. There is no need for our library to connect anywhere. Yeah, that's the thing. That it's completely local, completely software-based, and inside your application, sure, there are some other attacks against such a library. Because sometimes you don't really need to know the key. You only need to do the operation. I mean, if you need to sign something, you don't care really about knowing the key. If you can sign some data using our library, then you don't really need the key. So therefore, some other protection mechanisms are useful on top of this whitebox library, such as debug protection and so on, integrity checkers. Different kinds of other technologies are useful, but the key will be protected no matter what.
Do you mean attacks like man in the middle?
Sorry?
Do you mean attacks like man in the middle?
Not. Well, man in the middle is already something at a higher level, at where if you have a communication, when you have a communication, then there could be a man in the middle. In this case, there is no communication yet. This library is used to encrypt data for communication. So and that depends then on your protocol security, how you exchange keys, whether this man in the middle is possible, whether you do certificate pinning or such things. That would prevent man in the middle type of attacks. We care only about protecting the keys when they are used on the device. It's more on a lower level than the protocol design. So this is really when everything else has failed on the device. If the attackers have gotten to your device, then they still can't get to the actual key.
Is it usable only on Windows?
Sorry?
Is it usable only on Windows?
No. Sure. This AES Finder, the breaking tool, that was only Windows, but this library is usable anywhere where you have a C++ compiler.
Does it need it on other platforms? only Windows is so.
No, Windows has nothing to do with this white box library. Windows is just my preferred operating system. but the library itself, or white box technologies in general, they are not really platform specific. They don't need any hardware support or operating system support. They are just mathematics essentially.
Do you have support for different programming languages, not just Java? Is it like
Well, the core is a C++ library. So it's a static library which you link to your application, and Java support is built on top of it.
Yeah, I mean like SDKs. Do you have like SDKs for different languages, or
Well, if your language can call C API, then you can deal with it.
integration? So you don't have like.
We don't have nice language bindings for Rust or Go
but we
or
can-
whatnot. So
But it's easy to work with. So.
yeah, that's we are not a big team, so we focus on the security and then build as well. We have a WebAssembly version as well and JavaScript binding, so you could do it. You could use it on the web.
So it is completely impossible to reverse engineer your.
It's completely possible to reverse engineer. You can go wild and try to understand what's going on there.
So you
The task of this is to prevent you
100%.
from getting the keys.
100%.
Hmm?
100% that it's impossible.
100% reverse engineerable. Sure, I mean, programs are just area of bytes. So you can look at every byte and try to understand what's going on there.
Yeah, my question. So, if I decided to build some custom POS system, and where your kind of product or where your piece lies, or how to interact with it, when the interaction with the client happens. So they come to you and say, oh, we want to build a piece, and you, okay, you need kind of this library, custom library, maybe. Or how the process looks like, where the client
How the process works for you when you want to...
like for a client who decided to build something with you.
Okay. Yeah, if the client wanted to decided to use something like this, then there was this. This is from our web portal where the customer goes in, and well, this is the new version. They build this schema which they want to build. This one is an example for a fintech application. There's some output key derivation schema and some key agreement algorithm. Here is the key generation and the key agreement, and some unwrapping with AES and output key derivation, pin encryption, HMAC, and some BCDSA signature. So the customer who wants to do some of these operations, they come to the website, they build their schema, they say submit, and they'll get the library, a package which contains the library with this particular implementation, and then they can just integrate that library in their code, and that's it. They can use it. So they don't have to tell us any keys or any such thing. If they need, for instance, to embed some static key in their application, we give the tool as well, where you supply the plaintext key, and the tool produces a protected version that you can embed in your application. So again, the tool doesn't call home, doesn't connect to our servers or anything. It's completely offline product. Once you get it, you can use it and embed it in your application.
So the idea behind it, it's very strong obfuscation?
Yeah, you can say like that. I mentioned, when I agree that it's obfuscation, it is a sort of obfuscation, a very strong one and very tailored to specific cryptographic algorithms. It doesn't, for instance, you couldn't get a white box AES implementation by running a standard obfuscation tool over plain implementation of AES. You could obfuscate it, but all the typical attacks, the side channel attacks on white box, specifically on AES, they will break any such obfuscation. They will not notice even that there is an obfuscation. They're just statistically collecting traces from memory and using those some differences in bytes in that trace, and they will not notice that there is an obfuscation.
Yeah, but given that I can read memory and all the trace execution, etc. at the time, how can we make sure that I actually don't really realize what's going on? Like,
It's not so much about you realizing, not realizing what's going on, because what's going on is similar to what I showed in this small example, that there are some mathematics, and for you to actually get to values, to real values, you have to do some mathematics, which are, well, more or less difficult. And I mentioned fully homomorphic encryption. It is still kind of theoretical field, and the performance of provable algorithms is still insufficient in most cases in real world. So these theoretically secure algorithms, they can be used for some special subsets of applications, but for instance, if you need to sign something with RSA in 200 milliseconds, then fully homomorphic encryption will not help, because it will take seconds to do it, or more than seconds. So therefore, what we do, we use as much as possible, as secure as possible techniques, and to reach some acceptable level of security. Let's say, I can maybe tell our 3 levels that we, or 4 security levels. 1, key is not clear in memory. 2 was, okay, it cannot be broken by publicly accessible tools. And 3, it will withstand 2 weeks of expert security lab evaluation. And the 3 is typically what we stop at. The 4 is we cannot break it. And 5, we can publish and nobody can break it. So we would aim at 5, but that is still some way off.
So theoretically, there is enough data in the memory for the key to be reversible and theoretically, there is enough data in memory for the process to be reversible. Is that correct?
Sorry, there is.
Like,
I'm not hearing that well. So.
Yeah, sorry. Theoretically, is there enough data in memory for the process to be reversible?
No.
Yeah. Yeah. Okay. Sorry. Theoretically, could it be possible to reverse the process if someone devoted like a lot of time and it was a state level actor?
Which process?
Like your whitebox encryption, the work the library does.
Yeah. Okay, reversing. There could be several things that could be understood as reversing. One is like if you have an encryption, then you could try to do a decryption, but that's probably not what you mean. You probably mean understanding how this whitebox works.
I mean, like, in the example you gave, for example, you sent the modified A and B values with some unknown values in it that make them like unequivocal. My question is, could it be possible to essentially find out the original values, the original unencrypted values, even
in that example, no, because in that example,
no, because there's an outside force that has the values and they're never sent to the actual machine learning processing. My question is, with your library, is it theoretically possible to reverse like we have done and get the values?
Let's say there have been very few moments in time where we had reached level 4 in our algorithms. So level 4 being that we cannot break it. Typically we can break our own stuff. We know how, but it is extremely difficult in many cases. So you have to, it's a combination of understanding the code structure and then understanding where you have to read which data and combine the data in what way, so that you could do some mathematics that reveal eventually the real data. So it is difficult. I wouldn't say it is theoretically possible. Yeah, we know how to break our own stuff. So yes, it is possible. We are not there yet. I mean, even this fully homomorphic encryption, and none of the cryptography is theoretically possible. We just need very large resources. So given time, you can break everything. So, and that's the whole point of protection, was to give enough time for the original authors to survive up to some next point. When you rotate the keys, when you rotate the library, so there's some time limit which this library has to survive.
Thank you very much.
Yes, how do the software library compare to hardware solutions?
Yeah.
like enclaves?
Great question. The software library, well, let's say hardware on Android, you have the key store. On iOS, you have these secure enclaves. There are two main differences or two main advantages for the whitebox library, and there is probably also a disadvantage. Disadvantage, I'll start with the disadvantage, and that is that the code lifting is difficult with hardware. You can't just extract keys from your device. Software is just software, it's just bytes. You can copy it over and try to use it somewhere else. So that's the disadvantage. In that sense, hardware is better than software, because you can bind something to a particular device. With regards to advantages, there you have the hardware typically supports a limited set of operations. You can do encryption, signing. On Android, you can do unwrapping as well, but that's about it. You don't have key derivations, you don't have key agreements. So if your protocol requires some of those, then you are out of luck. Your hardware doesn't support it. And another thing is that you can, with software protection, you can embed a secret in your application. If you need some kind of attestation key or something like that, that you need to convince some third party that you are a legitimate application, you can't do it with hardware, because hardware is not part of your application when you deliver the application. So therefore, embedding secrets and wide features that those are.
Are there hybrid solutions that use both?
Not that I know of. No, I think if somebody wanted, well, okay, there was kind of a hybrid solution delivered by a company called Trustonic some years ago. They were trying to market their own implementation of the Trust Zone operating system and offer third parties to write these trusted applets, trusted pieces which could run in this TEE. And then for those devices which did not have the TEE or didn't have access for third parties to TEE, they licensed our technology to run that same trusted application in software only. So it was kind of, their solution was kind of hybrid, but not exactly that working together, hardware and software protections. But in this case, it was either or, either completely in hardware or completely in software.
Yes, thank you.
You mentioned that zero-knowledge proof is actually not the case, but have you tried to research the topic of zero-knowledge cryptography and actually apply it?
Well, I personally have looked at the zero-knowledge proofs.
Yeah, but I mean zero-knowledge
How can we apply
cryptography
it?
in the wider aspect. This is so not only about proofs, right? It's also about kind of making some calculations anonymously.
No, okay, no, probably.
It's
Probably the short answer is no.
It's quite a vast topic. I mean,
It is a vast field, and it has some promises and it has some solutions, like some cryptocurrencies use the zero-knowledge proof stuff. It's just that what I do professionally is not exactly related to that. We are a bit lower level, if you will, because zero-knowledge proofs are already higher level algorithms on top of...
yeah, but again, not saying about proof, but about zero-knowledge cryptography as a vast field, right?
Okay.
Because it gives more options rather than just providing proofs.
Okay, what I can say is that the technology that is used, or set of technologies that is used in white box implementations, typically can be used not only for cryptography. This is in fact how we started. We didn't do white box cryptography in the beginning. We used we did copy protection, and that meant that we had to take any arbitrary program, convert it into some obfuscated form, and do calculations with any data and any calculations, and do something to protect that software. So the underlying technologies can be used to protect any data on, or any operations on any data. So in that sense, it can be used for zero-knowledge cryptography or for any other type of calculation. But it's just currently in the state of our products, this is what we have.
Because this is pretty much seems the way to go. if you like trying to reach the fourth or the fifth.
Yeah, yeah, we
stage is
regularly
pretty much the way to
we
go.
regularly get there for a week or a month or two, and then we find a way.
Mhm.
But yeah, the important thing is, of course, that we keep ahead of competitors and attackers. Any other questions?